Hey everyone, today we're going to further on using our application of our ideal gas law that we've been working with. In the past several lessons, we learned what the ideal gas law equation was. We also learned how can we use it to find density and molar mass, and today we're going to apply it to something that we've been doing in all of our past chapters, which is stoichiometry. As a general reminder, the ideal gas law is PV equals nRT. If we recall, P stands for pressure. And remember, our pressures for the ideal gas law should always be in ATMs. V stands for volume. And remember, our volume is always in liters. N stands for moles. R is our gas constant, which is 0.08206. And it's the whole reason we have to have things in liters and ATMs. And then our T stands for temp. And remember, our temperature should always be in Kelvin. Just as another reminder, remember that Kelvin is going to be your degrees Celsius plus 273.15. If you use 273, that is okay. There'll be a slight discrepancy in answers, but I should see in your work that that's what you did. As a reminder, in this section, we're going to connect this with stoichiometry. Now, we can both use ideal gas law and stoichiometry to find different values for compounds, such as grams, moles, liters, etc. However, what equation and mathematical process we use is going to depend what is given to us in the equation. So there are two scenarios. If we're given moles or grams in the problem, or if we're not given moles or grams in the problem. So the first scenario is if we're given moles/grams in the problem, I'm going to tell you that you are typically going to start with stoichiometry. And the whole point of this is if you are actually given grams, it's not specifically written here, but you want to get grams into moles first using molar mass. Once you get your things into moles, then we're going to use our mole ratio. Remember, this comes from our balanced chemical equation. We're going to use that mole ratio to determine how many moles there is of the other compound, because remember, mole ratio allows us to convert between different compounds. From there, we're actually going to use the ideal gas law and information in the problem to determine what we're trying to find. So, for example, we would use the ideal gas law if we're trying to find pressure or volume or temperature. If you are given a problem and you are not given moles/grams, what you're going to see mathematically is you're going to start with the ideal gas law first. We're going to use the information from the problem and the ideal gas law to determine the moles of one compound. Once you figure out the moles, then we're actually going to use stoichiometry to determine what we're trying to find. So maybe we're trying to find grams of the other product. So that's going to help us there. I'm going to do an example of each of these scenarios, and then for homework, I'm going to have you do an example of each of these as well. So our first example says, if an airbag has a volume of 36 liters and is to be filled with nitrogen gas at 1.15 atm and 26 degrees Celsius, how many grams of NaN3 must be decomposed? And this is actually a common equation used for airbags. And our balanced chemical equation is already balanced for us. First thing that we need to know is, am I given grams or moles? And you're going to read this problem and realize you are not given grams or moles. So if not given grams or moles, we're going to start with our ideal gas law. So here we're going to start with ideal. If we look at our ideal gas law, which is PV equals nRT, we have our pressure that is given to us is going to be 1.15 atm. And notice this 1.15 atm goes with nitrogen gas, which is N2. Our volume is going to be 36 liters. Notice this volume also goes with nitrogen gas. Our number of moles, we do not know it because it does not give us anything. Our R constant is always the same, 0.08206. And then our temperature is given to us in degrees Celsius, so we need to add 273.15, and we should get 299 degrees, 0.15 Kelvin. From there, we're gonna plug this into the ideal gas law, and this works because every single one of these values goes within the compound N2. So we're gonna plug in 1.1536 equals X, because that's what we're trying to find, 0.08206, and then we're gonna plug in 299.15. From there, we're going to go ahead and multiply these two, and we get 41.4 equals, and then we're going to multiply the 299 and our R factor, and we're going to get 24.548249, and then we multiply that by X, so there's an X on the end. From there, we're going to divide by the number that's attached to the X, which is our 24.548249. And we're going to see that my X value equals 1.686474665. And this is where labeling comes into play. Because if we don't label, we're going to think that we're done, or we're going to think that we already have moles of a different compound. So we want to make sure we label correctly. Here, we're trying to find moles, so that is my label. And we also have to realize we're finding moles of N2. So N2 is also part of our label. Once you find moles in the ideal gas, we need to then use stoichiometry, because it doesn't want us to find moles or grams of N2. It wants us to find grams of NaN3, which is a completely different compound. So we're going to start with what we found in our ideal gas law. Remember, we do not want to round until the end, so I'm going to start with the whole number to begin with, because this is moles of N2. Then since we're already in moles, we can go straight into our mole ratio from our balanced chemical equation. If we want to cancel out moles of N2, we're going to put 3 moles of N2 on the bottom. Again, remember, I get the 3 up here from the balanced chemical equation. And then on top, I'm trying to get to NaN3. So here, my balanced chemical equation, I see that's 2 moles of NaN3. But it doesn't want moles of NaN3, it wants grams. So again, I'm going to go from moles to grams, and we learned that we use molar mass for that. So to cancel out moles, 1 mole of NaN3. And then our grams, if we find the molar mass of NaN3, it's going to be 65.011 grams of NaN3. Now remember, if we do grams over moles, it's always going to be 1 mole, because that's molar mass is grams per mole. When we actually go to solve this, multiply what's on top and divide what's on bottom, and we round to the correct number of sig figs, which is 3, you're going to get your final answer to be 73.1 grams. And then since we're working with multiple products, we have to have a label NaN3. For your homework, I have given you a similar problem. I would like you to put this problem in your notes, and I'm actually going to check for completion for this tomorrow. This is actually part of your homework, so this is your more practice. Here's my second example that I'm going to walk through. My second example says calculate the volume of dry CO2 produced at body temperature, which is 37.0 degrees Celsius, at 0.970 atm when 24.5 grams of glucose is consumed in the reaction. And the balanced chemical reaction is given below. So first thing that we have to ask ourselves, are we given grams or moles or are we not? Here we're going to see we are given grams or moles. We're given 24.5 grams of glucose. So when we're given grams or moles, we're going to start with stoichiometry first. So here we're going to see that we're starting with 24 0.5 grams of glucose. And we want to change this into moles first because we can't do anything unless we're in moles. So grams to moles, we're going to use molar mass. We have 1 mole of glucose is actually equal to 180.1548 grams of glucose. Now the next step is we want to actually change this grams of glucose to a different compound. And to figure out what compound we need, we have to make sure that we read the problem carefully. We want to eventually find the volume of CO2. So CO2 is the compound that we eventually want to get to. So we're actually going to use our mole ratio to get to moles of CO2. Again, if I have 1 mole of glucose over here, I need to use mole of glucose on the bottom, and then I want to get to moles of CO2 on top. Again, we're going to fill in our moles using our balanced chemical equation. We should see that CO2 is 6, and then our glucose is 1, because glucose is C6H12O6. Now, a lot of people will make the mistake and they'll keep going until they get to grams, but we're going to be using the ideal gas law next. And so we actually want to stay in moles, and so we'll actually end up equaling this out. 0.815964938 moles of CO2. Again, labels are super important so we know where we stand. Once we actually find moles of CO2, it will allow us to actually do our ideal gas law. If we look at our ideal gas law, we have PV equals nRT. So our pressure is 0.970. Our volume is actually what it's asking for, so we're going to plug in X. N is our number of moles, which we found previously, 0.815964938 moles of CO2. R is always going to be the same. It's our R constant. And then T is in temperature. So we're going to see I'm given 37 degrees Celsius, so I need to add 273.15. When I add that and change that to Kelvin, we actually get 310.15. And then we can actually just go ahead and solve this. We're going to see I get 0.97x equals 20.76704935. We're going to divide by the number attached to x, which is 0.97, and we're going to find out that x equals, when rounded to correct number sig figs, which is 3 sig figs, should be 21.4 liters of CO2. Again, this works because everything that I'm given for the ideal gas law is actually for CO2. The volume of CO2 produced at the body temperature for CO2, the pressure for CO2. So this all works. Here is a practice problem where you are given moles or / grams, and you need to find another product. Again, similar to the one we did last, but slightly different. I want you to do this for homework, and I'm going to check to make sure you have this done. If you have any questions, please make sure that you ask, because that's the end of my lesson, and I hope you guys have a great day.